our goals for today are, first of all, to get an introduction to exponential functions. What are they? And maybe more importantly than what are they, how do we understand how they're different from linear functions? So we spent a lot of time in the first portions of the course studying y equals mx plus b style linear functions, right? Linear, y equals mx plus b. And in this chapter, we'll look at exponential functions. It has a different equation template, y equals a times b to the power x, like that. And so I think we can tell just by looking at the formulas that these are different kinds of functions. But again, we want to take those different perspectives, not just the perspective of the formula, but also the perspective looking at a table of data. How can I tell that this is exponential rather than linear? Also looking at a graph. How can I tell that something is exponential instead of linear? And then we'll compare and contrast the parameters in these. So the m and the b of the linear equations, or the two parameters, the slope and the y-intercept. And then for an exponential function, there's an a and a b. And unfortunately, the b means different things in these two different cases. Sad bit of notation. But we want to compare and contrast the meanings of those numbers that go into these formulas. And in particular, the key role here is played by a quantity called the base of an exponential function. So we want to ask, how is a base for an exponential function similar to the role that slope played for linear functions? And then what are the important differences in how we interpret those two quantities? So that's what we're going to tackle with exponential functions today. This first activity gives us a contextual situation. Suppose that we have $20,000 and we can do one of two things with it, right? We can either invest it in a mutual fund that earns 8% annual interest, which it's a pretty good mutual fund, actually, in today's market. Or the other option with what to do with my $20K is I can go buy a car for $20,000, and that car's value is going to depreciate by 12% every year. And so the question is, in each of these two situations, the investment, which is my I of t function, and the vehicle, the value, v of t, if I'm buying a car, value of that car, how do those values change over time? And so in this activity, the first thing you're asked to do is the numerical work, the data table work. To first of all, take a look at t measured in years versus I, the value of my investment, which is going to be in, let's see, we could measure this in dollars, but maybe we should measure it in thousands of dollars, just so that we have a little bit nicer numbers. So in year 0, my investment is worth $20,000, and then your job is going to be to fill in the rest of the table for years 1, 2, and 3. Right? And then similarly, for the situation in which you decide to buy the car instead of invest in the mutual fund, same thing. Just instead of being a table for I of t, that would then be a table for v of t. And so you'll develop a data table for each of these two situations. And then the really interesting parts, right? Once we've understood these situations numerically, we want to understand them graphically. So I would actually encourage you here to do part D before you try to do part C. Because part C is the one that I want us all to kind of talk about the most together. So do part D first, get that graph, and then do part C second, after you've done parts A and B first. Does that make sense? So A, B, D, C. So the reason that I asked you to do the data tables in this problem first, and then do the graph second, and then think about the formula last, is because I want us to really understand where the formulas that we're working with come from. Like why must the formula for this behavior look the way that it looks? And in particular, why does it look different from the formulas that we would expect to see for a linear function? So in this problem, we have an investment that starts out at $20,000 and then earns 8% every year, right? So at the end of the first year, 8% of that 20,000 is 1.6 thousand. Added into my 20 gives me 21.6 thousand. At the end of the next year, we've taken 8% of 21.6 this time and added that amount into the 21.6 to get the new total. And then we'll take 8% of that amount and add it in and get the next total and so forth. Meanwhile, if we invested that 20,000 into the car instead of the mutual fund, right, we start out in my first year of owning this car, its $20,000 value is going to depreciate by 12%. So 12% of that 20,000 is 2.4 thousand. And because we're depreciating, what do we do differently here? we subtract from 20 instead of adding to 20, which is what we did when we had an appreciating value. Right? So subtract 2.4 from 20, we get 17.6. So at the end of the first year, my car is worth $17,600. And then in the following year, the amount by which it depreciates is 12% of the 17.6, which is about 2.11. Right? And then we'll subtract that amount from 17.6 and keep going. Right? So what we ultimately end up seeing here are these two different kinds of trends. Here's my investment. Here's my mutual fund. And as time goes on, how would you describe the shape of this curve? This is my y equals I of t. What's important about the shape of that curve?
It's not straight.
It's not straight. So first important observation, it's not a straight line. If it were a straight line, what kind of a function would we be talking about? Linear function. Right. So observation number one is unless we know our function is linear, the graph will not be a straight line, and vice versa. Right? Linear functions are the only kinds of functions whose graphs are straight lines when we draw them on graph paper in which distances are represented by differences. Right? So there's the same amount of distance on this graph paper between 1 and 2 as there is between 2 and 3, as there is between 3 and 4. I'm being very careful to hedge here because there are different kinds of graph paper in the world. Maybe we'll get an opportunity to look at a different kind today. But on regular, normal graph paper, the way that we normally graph stuff, linear functions look like straight lines. Nonlinear functions don't. So we don't have a linear function. What else would you say is important about the shape of this graph, specifically how the shape relates to the observations that we were making a minute ago about how the amount of change itself changes from year to year? In the first year, my investment earns $1,600. In the second year, it earns $1,700, give or take. In the next year after that, it probably earns $1,800 or $1,900. So what is happening to that difference from year to year? The amount by which my investment is increasing every year itself is increasing every year. So how should we expect that to be reflected in the shape of the graph? Let's think about this 1.6 number, this amount of money that my investment earns in the first year. That 1.6 is the difference between the $20,000 at the beginning of the first year and the 21.6 at the end of the first year. 21.6. And so if I take my 2 points, right, here's my point at the, my point at the end of the first year. Here's my point at the beginning of the first year. That 1.6 is the vertical distance between these 2 points, right? It's the amount of money, y-axis, that I gain in the first year. How many years does it take me to earn that 1.6?
2 or 1?
Yeah, it's at the end of the first year, so it's just 1 year. Right? So we'll say $1.6 thousand over the course of 1 year. If I wanted to turn that into a rate, how many thousands of dollars per year did I earn during that first year? What would I do with these two numbers? To get thousands per year, what would I want to do with these two? Divide them. 1.6 thousand divided by 1 year. Yeah, I get 1.6, right? 1.6 thousand divided by 1 year. We'll just simplify the arithmetic. $1.6 thousand per year. But when I've divided those two things, what kind of a quantity am I now talking about on the graph? Or what kind of quantity that we knew from chapter 1 do we get when we take and divide a difference in y values by a difference in x values? I get an average rate of change. On average, during that first year, my investment in this mutual fund is appreciating, is increasing at a rate of $1.6 thousand per year. That's an average rate of change. This is AV 01 for my I function. Right? And now that we know that it's an average rate of change, how do we see it on the graph? It's a slope. It's the slope of, it's the slope of the line that connects those 2 points. Yeah. So let me try and write that in here in a way that we'll be able to see it. The slope of this little line segment is 1.6. Great. So then what do we think is going to happen over the next year? What's going to happen to the average rate of change on the interval from 1 to 2 compared to the interval from 0 to 1?
It'll be higher.
It's higher. So what's happening to the slopes? They're getting Steeper. Exactly. They're increasing, they're getting steeper. So I remember when we were first talking about average rates of change and slopes, and I kind of dropped that little teaser that, well, they themselves are rates of change, but they themselves in turn can change. And here's such an example, right? Slope here is 1.728, so it's steeper. So the graph is getting steeper just a little bit. It's kind of not quite perceptible, but then if we go one more year out, we can tell that the slope over the next year is going to be even steeper than the slope over the first couple of years. So what are the two things that we notice about this first graph, my I of t graph? I want to talk about both its slopes and also how those slopes are changing. So first of all, what is true about all of the slopes anywhere that we measure on this? They're all going to be positive. Why? Right, because the value of my investment is always increasing over time here. So I'm always going to have more money in year x plus 1 than I have in year x, right? Because I'm always earning over the course of that year. Its slopes are always positive, but then what are they also doing? According to the pattern that we're seeing here. 1.6, 1. Yeah, the slopes are positive, and the slopes themselves are increasing. So I actually want to emphasize that here. I'm not saying that the function is increasing, although it is, but I'm also saying that the slopes are increasing. And what feature of this graph, and I think, Tyler, you mentioned this, what feature of this graph does that correspond to? Visually, what does a graph look like if its slopes are increasing? How is it bending?
In a concave way.
It's bending in a concave way. And just to emphasize concave how, usually we add an extra word on the end of that. I would say that it's kind of bending upwards in a way, right? If it were raining on top of this graph, the rain would tend to collect here in the middle rather than run off, right? And so what we typically call that, we call it concave up. Exactly. Its concavity is that it's bending upwards. Its rates of change, its slopes are increasing as we go from left to right on this graph. So, okay, let me ask this then. Which of those two properties, so the property that its slopes are positive and its slopes are increasing, which of those two is not true for the purple curve?
Up, because it's not up, it's going down.
So let's do the same exercise that we did here, right, with the data that's down here. In the first year, we lose $2.4 thousand in the value of my car, 12% of the original $20,000, right? And so that then becomes a slope. I'm going to erase the annotations that we had here just so that we can see what we're doing. So in the first year, we go from 20,000 down to 17,600. That's this point right here, 17.6. So if I'm finding the average rate of change, we've lost 2.4, and we've lost it over that period of 1 year, again. What is the average rate of change going to be in this example? AV01. Y2 minus Y1 over X2 minus X1. Yeah, what am I missing? I'm missing a sign right there. Right. So the average rate of change here is going to be negative 2.4. We've lost $2,400 over the course of that 1 year. And so we simplify that ratio. Our average rate of change is now minus $2.4 thousand per year. Right? So my first average rate of change is minus negative 2.4. What's the next average rate of change going to be, according to the work that we did over here? Minus 2.1. So which is bigger? Negative 2.4? Which is greater? Let me say that. It's a better way to say it. Minus 2.4 or minus 2.1? The greater number, in the sense of further to the right on the number line, is minus 2.11. Right? So my earlier average rates of change are large negative, and then they become less negative, and less and less and less negative, and so they are increasing. They're getting closer to zero, right, along the way. way. They start out large negative, and then they increase as we go along. So, what can we say about this purple graph? Its slopes are what?
Negative.
The slopes are all negative. Why? Why does that make sense in the context?
Graph is going down.
The graph is going down. Why does it make sense with respect to my new car?
Appreciate it.
It's depreciating. It's losing value. It is apparently not yet a collector's item, right? Every year it's losing some of its value. So it's a decreasing. The value is a decreasing function of time. So the slopes are negative. But how are the slopes changing? The slopes are increasing. And if the slopes are increasing, what did we say that means about the shape of the graph? Yeah, this graph is also concave up. Right? If it were to rain on top of this curve, the water would tend to collect rather than run off. Right? Another way to think of it is if I'm in an airplane flying along this curve, there's a wing and here's a tail. I can't draw airplanes very well, but whatever. If I'm in this airplane and I'm flying along this curve, is it going to feel like I'm pulling back up on the stick or pushing down on the stick? Is the airplane's altitude accelerating upwards or is it accelerating downwards? Yeah, it's accelerating upwards. I'm going to feel like I'm getting pressed down into my seat. I have extra G-forces on me if I'm riding in this plane, compared to if I were riding on a plane in a concave down fashion, which I don't think I would like to do very much. Right? In this plane, if its altitude is doing this, now it feels like you're nose diving into the ground, right? You're getting pushed up into the ceiling instead of down into your seat. So some of the differences between concave up and concave down. So whether a function is increasing or decreasing, we can tell just based on the signs of its slopes. Negative slopes for decreasing functions, positive slopes for increasing functions, right? But how its slopes are changing gives me different information about the shape of the graph, right? When the slopes themselves are increasing, my graph ends up looking like it's concave up, like this example, and this example. So what would my slopes be doing for a curve that looks like that? First of all, would the slopes be positive or negative?
Still be negative.
Slopes would still be negative because decreasing. But would the slopes be increasing or would the slopes be decreasing? They'd be decreasing. So they start out, it looks like a very sort of shallow slope, close to zero but negative. But then as we go further and further along, my slopes are getting steeper and steeper negative. So they're becoming more and more negative, they're decreasing. Right? So just as a way to tie a bow around these observations, and this is something that, put a paper clip in this in your notes for when you take calculus. Whether a function is increasing or decreasing and whether it's concave up or concave down are two independent things, right? One of them has to do with whether the slopes are positive or negative. And the other has to do with whether the slopes are increasing or decreasing. And each one of these has different graph shape associated with it, right? Positive and increasing looks something like this, right? So we would have a graph that looks like it's concave up and increasing, right? Whereas negative slope and increasing slope, that would be like this example, right? Where we get a decreasing graph, except it's still concave up. Decreasing, concave up. And on the flip side, positive slopes that are decreasing, well, that might look something like this, right? We're still increasing as we go from left to right, but now my slopes are starting out large positive and becoming less positive, so the slopes are decreasing. And in that case, we say the graph is concave down. And then same thing on the other side. This is my airplane that's nosediving, decreasing, concave down. So those are the four basic, what I would call second-order shapes of graphs. And I call them second order because first order is kind of an increasing, decreasing question. Second order adds the concave up or concave down question. So last thing we need to attend to here is how do we come up with a formula that describes each of these two different types of behavior? And the first thing that I would ask us to do, and this is something that anytime I talk about percentage increase and decrease with any crowd, when we learn how to calculate percentages increased and decreased, usually it's a two-step process, the way that you did it here, right? If I want to increase this quantity by 8%, I do two things. I multiply, and then I add. If I want to decrease this quantity by 12%, I multiply, and then I add, or subtract in this case, I guess. So what I want us to do is I want us to think about that as a single step instead of as two separate steps. So I want to unpack this first step from 20 to 21.6 for a second. What did we do? We did 20 multiplied by 1.6, multiplied by 0.08, and then we added 20. How do we skip that step? We factor out the number 20 from these two terms, because it's a common factor, right? 20 times 0.08 plus 20 times 1. Factor out the 20, and the cofactors are going to be 0.08 and 1, respectively. We have that plus sign in between the two of them. And so sure enough, Max, just as you said, we could think of this instead as multiplying by 1.08. So that's how we increase a quantity by 8% in a single step, right? Rather than multiplying and adding, or maybe another way to say it, rather than adding at the level of the dollar amounts, we add at the level of the percentages. Right? We take 8% of the number, and then we add it to 100% of that number. And in total, we have then increased by 108% of that number, which is what this 1.08 is doing for us. And this is what helps us get to a formula for this behavior, because that's repeatable. To get from this number to that number, I'm just multiplying by 1.08. And then to get from that number to the next number, I'm multiplying by 1.08. That's the advantage of this, is we don't have to go back and then rethink, okay, now I'm taking 8%, but it's 8% of a different base amount this time, and then I have to add it to that different base amount this time. This short circuits all of that and just says all we have to do is multiply by 1.08. And so after 1 year, this 21.6 came from 20 times 1.08. 20 times 1.08. And then a year later, we're multiplying that by 1.08. So 20 times 1.08 times 1.08 is what we have at the end of year 2. And then if I multiply that by 1.08 again, 20 times 1.08 times 1.08 times 1.08, and that starts to get exhausting to write. So how do I write 20 times 1.08 with 3 repeated factors of 1.08? I use an exponent, power of 3, exactly. 1.08 to the 3, and so on and so forth. Right? And so, in general, I of t, if I know how many years I have gone by, how do I figure out the total value of my investment in the mutual fund? 20 times 1.08 to the power.
T.
Yeah. 20 times 1.08 to the power t. Exactly. Right. And so right away, what we're seeing here popping out at us is a different kind of formula for an exponential, what we call an exponential function, right? And what I want to draw our attention to here are both similarities and differences between these types of functions and the linear functions that we studied in Chapter 1. So in this data, notice that there's a consistent kind of change that's happening in my t values, right? From year 0 to year 1, I'm just adding 1 year. Year 1 to year 2, I'm adding 1 year, and so on. So all of my consistent changes happening in the independent variable happen by addition. But all of my changes happening to my output variable are happening not by addition, but by multiplication or division. And that is the fundamental difference between exponential functions and linear functions. Because for a linear function, if this function were linear and I were adding the same amount to my t variable, what would I be doing to my I variable? I saw a couple of your models in this problem actually did this initially before you figured out that they were incorrect. let me say that again. If this were a linear function instead of an exponential function, what would I expect to see different in the ways in which my output variable changed when my input variable changed by a constant plus 1?
You'd be doing addition in the bottom.
I'd be doing addition in my other quantity instead of multiplication. So for example, let's imagine, I want to actually pick up on an example that I saw in one of your groups as I was walking around, right? Actually, I saw it in one way or another, actually in more than just, I saw it in both of your groups at some point. So the reasoning roughly went like this. In the first year, my investment gained $1.6 thousand. If this were a linear function, what would happen in the next year?
You'd add 1.6.
I would add 1.6 again, plus 1.6 in the first year. And then if this were a linear function, we would add 1.6 in the next year and get 23.2, which is kind of close to what we had in the exponential model, but not quite, right? It's about far enough off that, maybe you wouldn't be able to get Starbucks for a month or something. And then in the next year, we would do it again. We would add 1.6.
What is that called? Common ratio?
Common ratio. Well, we would call it a common ratio, that common ratio being the slope of that linear function. Exactly, 24.8. Right, and so this function would be linear because the same addition in the independent variable would be associated with the same addition or subtraction in the dependent variable. So linear functions relate addition to addition or subtraction, right? Whereas exponential functions intertwine addition with multiplication. And that is the difference. And as you might expect, if I look at the inverse function of this, let's do a quick call back to inverse functions. What would an inverse function to this look like? What kind of changes in the independent variable would be related to what kind of changes in the dependent? What happens when we invert a function? Y becomes t, t becomes y. And so for whatever the inverse of an exponential function is, it's going to relate multiplication in the independent variable with addition in the dependent variable, right? And that's the second half of our chapter. We're going to get to functions which do that. But again, inverses just represent the same kind of relationship, just with the roles of input and output reversed. Okay, and then just to finish this last example, what's different if I try to find a formula for this function instead? I'm multiplying by 0.12, but then I'm subtracting.
You're going to want to take it off take it away from 1.
Take it away from 1. So I had here 20 times 0.12, and then I'm subtracting that. So actually, yeah, I don't want to do this the other way around. 20 minus 20 times 0.12. And then again, we have that common factor of 20 in both of those terms. So we bring that 20 out, and my cofactor that's left over is 1 minus 0.12. So we start each year with 100% of the amount that we start the year with, and then over the year we lose 12%. And so how many percent are left at the end of that year? Right, 100% minus 12%, 88%. Actually, the author of this problem gives us that hint as part of the setup. Actually, it's part of, I think, one of the parts that I erased up here on the screen. If we're losing 12%, it means that we're keeping 88%. This, by the way, is another way to quickly compute discounts. If you're like shopping, right, and you see, 10% off. Well, I could take 10% of that and then subtract it. Or I can just think 10% off means 90% on, right? So if I'm buying something that costs $70 and I get a discount of 10%, well, I'm keeping 90% of the price, so 90% of 70 is 63, right? So 7 times 9. So that's the secret here, right? And so everything proceeds in the same way, right? Every year we're going to multiply by 0.88 rather than seeing this as two separate steps, because we're keeping 88% of the value every year. And so what formula would I then have for this relationship? I of t equals 20 times 0.88 to power t. And again, it's an exponential function because every addition of 1 in the independent variable is associated with the same multiplication by 0.88 in the dependent variable. The domain of any of these exponential functions is all real numbers. We can have any real number as the exponent up here, and we can get mathematically an answer. But practically, what would the domain be for this problem? where I'm investing when I'm 20 years old. I'm putting this $20,000 into either a car or a mutual fund, and then it sits in that account. What would the practical domain for this function be? Probably just positive numbers, right? Because we can't go backwards in time. I know that if we could go backwards in time, then the person who invested in this car would want to do so, right? Because, if you could just give me what this car would have been worth 10 years ago, I would have more money. Right? I could just take a time machine and I could go make a big profit. But yeah, practical domain for this is positive numbers. But the mathematical maximal domain is all real numbers. What about the range? I kind of talked to one of your groups about this. I want to go back to the graph. I want a less cluttered version of this graph because now all of our markings are on here at the same time. So if the domain of this graph, the domain of this function, is all real numbers, we can put anything we want to in for t. This graph will cover the entirety of the x-axis. Domain. I'm going to write that in interval notation. Minus infinity to infinity. What about the range? The question there is, how many dollars can this car be worth at any point in time? It can definitely be worth 20. It can be worth some of the numbers less than 20. Mathematically, if we continue backwards in time, how large could its value go? It could keep going, right? If we just keep increasing it by whatever the reciprocal of 0.88 is, that's how much it would increase by if we go backwards for a year, right? But if we continue to do that, it's just going to keep going up and up and up and up to the sky, right? So it doesn't appear that there's an upper bound on the range of this function, but what about the lower bound? How small can the value of this car get as we go forward in time? Let's say the value of this car falls to $1 at some point. What's the value going to be a year later? 88 cents. And then the year after that, it's going to be 67 cents or something, right? It's going to be some amount less. Is there ever a value that is too small for this car to be worth that value?
No, in theory.
No. If we have enough time, we can continue to lose 12% more every year until we get down to whatever that value is. So, but there is some limit. What is this car never going to be worth?
Zero.
It's never going to be worth zero. Because every year we're hanging on to 88% of the last value. So as long as there is some value, a year later, there's still going to be some positive value. Just 88% of what we had before, right? So it's never going to be worth zero. But it can be worth anything approaching zero. So the range of this function goes all the way up to infinity. It goes all the way down to zero, but does it include zero or not?
No.
It doesn't.
Bracket.
Open bracket, open parentheses for the bottom of its range. And so another way of writing the range is kind of putting this open circle there at zero and then shading the rest of the y-axis all the way up to infinity. So that's another way to view what the range of this function looks like. And that is common to all exponential functions that have the form y equals a times b to the t. As long as our value starts positive, so I'm going to stipulate here that a starts off positive. As long as the value of our thing starts off positive, it's going to remain positive. As long as I'm multiplying it, and by the way, we're also going to require that b be positive. There's a bunch of reasons why we wouldn't want b to be negative. Maybe we'll talk about those, if you're interested in between our class meetings today. But as long as the a and the b are both positive numbers, it means we have some positive value that we're starting with, and then every year it's either increasing or decreasing by a fixed percentage, right? And so if we start with positive value, we're always going to have positive value. And towards one direction, it's going to blow up to infinity, and towards the other direction, it's going to settle down towards zero. Does anyone know that the $64,000 word for the phenomenon where a graph infinitely closely approaches a line but never actually becomes that line? It starts with an A. Yeah.
No way.
Yeah, that's it.
That was
If I had $64,000 right now, you would get it.
just a guess. I just
Yep.
went with it.
And in fact, asymptote even kind of becomes a word in sort of popular culture, sort of something that gets as close as you can possibly get without actually getting there. This is in like classic Greek mythology, or Zeno's paradox. Zeno's paradox is, well, if I want to get from here to the door, then first I have to get halfway there, right? And then from there, I again have to get halfway to my destination. And then from there, I have to get halfway again. And from there, I have to get halfway again. And so it takes me an infinite number of halfway steps before I actually can make it to the door. How is that even possible when I only have finitely many seconds in which to do it? That's kind of a colloquial version of Zeno's paradox. But right, so this sort of conveys that information. We can get as close as we want to, and then the next year, or the next 1 unit on my x-axis, I'm going to get a little bit closer, and then a little bit closer, and a little bit closer. But I never actually get there.